Now that we've completed implicit differentiation, we are going to take a look at an application of that type of derivative called related rates. So up top on your notes, you see that there's a list of different formulas that you might need that for some of these problems. So we're going to be using a few of those today. And then there's also a list of steps that we're going to follow. So I'll kind of talk you through those steps in the first problem. First thing, but this is with any word problem, is identifying what you have and what you need. So in this first example, our step 1, air is being pumped into a spherical balloon. So we're going to be using the sphere information from up top at 10 centimeters cubed per minute. So our rates are going to be our derivative information, so d something over dt, because a lot of times we're working with time here. We want to calculate the rate at which the radius of the balloon is increasing. And then we're given the diameter. So we're given 2 rates and we're given a value for our diameter. So since we're getting air pumped in at 10 centimeters cubed per minute, that's our volume. We're going to call that dV over dt, V for volume. We're going to be calculating the rate of the radius, so we're going to call that dr over dt. And then we're given the diameter is 15 centimeters. Now, in this case, we really need the radius. So I'm going to cut that in half. We're going to be using 7.5 for our radius when we use our formula. And then our second part is setting up an equation. So since we're working with volume of a sphere, we're going to use the equation V equals 4/3 pi r cubed. And there's really nothing to plug in here because we have the 2 variables we need. What we're looking for is we're going to have the V and the R in there still when we take the derivative. And then we have information we can plug in later once we found that. So the key here, and I just put a little star at the bottom, every variable needs to get the implicit differentiation notation. So dx over dt, dy, in this case dr. We're going to first do dv over dt, which we'll be able to plug in. If you bring the 3 in front and multiply by the 4/3, we'll get 4 pi r, and then subtract 1 from your exponent, so squared. Next to the r, we're also going to be putting a dr over dt. That's what we're trying to solve for. So unlike when we did implicit before, where we just put it with y, we are now putting that notation with every variable that we take the derivative of. It's a little bit new, but not terrible. And then so that was actually really step 3, just to label our steps. And then we're plugging in the remaining info and solving. I'm not going to label the steps on every one, but just for this first one so that you can see what's going on. So we know that dV over dt was our volume rate. We're plugging in 10 there. We know that our radius at this point is 7.5, so we will plug that in. What we're trying to solve for is dr over dt, so we are going to leave that out and calculate this. So if we calculate 4 pi times the 7.5 squared, we get 217 pi. And then we'll divide that. So you can write your answer in 2 ways. You can leave it in terms of pi. This will be centimeters per minute. Or if you calculate that, it will come out to 0.015 centimeters per minute. And that is the rate that the radius is changing at that particular instant. And these rates can increase or decrease depending on the radius or diameter that you're working with. So that process we're going to use again. We're going to switch over and look at another 3-dimensional shape of cylinder. What's going to be the same kind of rules apply. We'll identify what we have and what we need. We'll set up the equation and do our implicit differentiation to come up with our result. All right, so for the cylinder, I'm just going to draw a picture for this. My spheres usually don't come out very good, so I chose not to go with that on the last one. But with the cylinder, we have the height and the radius are the important parts. So let's see what they're giving us. They're giving us the base radius is 2 meters. This actually will be giving us some extra information, but I will identify it. We have a height of 4 meters for the entire cylinder. And then it's telling us that water is being pumped into the tank at a rate of 2 meters cubed per minute. So anytime you're seeing that cubic notation, that's our volume rate. So this case we'll do dV over dt again for volume is equal to the 2 meters cubed per minute. Find the rate at which the water level is rising. So the water level is really our height. So we're going to be doing dH over dt. That's our question mark. And then it says when the water is 3 meters deep. So we're given two different heights, which means most likely we're actually not going to be plugging in that information. It's a little bit extra. If we go to our volume of the cylinder, which I can scroll back up real quick. Now we're looking at the cylinder instead of the sphere. So right here, volume of the cylinder is pi r squared h. Now, as of right now, we have 3 variables in this, which is okay, but we don't have a dr over dt. We don't have a rate for the radius. So we want to keep the volume and we want to keep the h because those are the 2 rates we're exploring. So we're going to plug in r. That actually makes the derivative a lot easier to work with. So we've identified, we've set up our formula. Now we're going to take the derivative, our third step. dV over dt equals 4 pi. The h goes away, but we're going to put dH over dt with that. We know that dV over dt is 2. And if we solve that, we divide both sides by 4 pi. An exact answer of 1 over 2 pi meters per second, or 0.1592 meters per second. So the process for these is all really the same. It's just the setup of your formula is going to be different depending on the scenario that you have. And that's usually the hardest part of these, is getting it set up. Finding the derivative and plugging in your values should be the easier part. Okay, that's where we're going to stop this first video. We're going to take a look at a second one to do some other examples.